Today in class we looked at Unit 7, Lesson 1, Children's Barnyard. In the Ready section of tonight's homework, we're focusing on finding the area and perimeter of different polygons. When we look at the given figure, we see that we are given 4 of the side lengths of this figure, but we're missing 2 of the dimensions. We know that in order to find the area of a polygon, we need to add up all of the total dimensions of the figure. So the first thing that we need to do is find the length of these 2 missing sides. If we take the entire figure and we split it into 2 smaller rectangles, we can use information that is provided to find these missing side lengths. And this is similar to what we worked on in class today. We know that if we look at the left-hand rectangle, it's got dimensions that are 10 feet by 12 feet. We know that opposite sides of a rectangle are congruent. So if this side length is 12, we know that this side length is also 12. If we take the entire side length here of the figure, which is 20 feet, and we subtract this 12 that we know, what we're left with is 8 feet, and that is this length. Again, knowing that opposite side lengths of a rectangle are congruent, that would tell us that this side is also 8 feet. If we know that this side of the smaller rectangle is 4 feet, then we know that this side is also 4 feet. And if we split this left-hand rectangle like this, then we can determine that this side length is also 4 feet. The reason why we want to do that is because we're looking for this length. Now we know that from the very top of this figure all the way to the bottom is 10 feet. We know that because this entire side length is 10 feet. So if we take the entire 10 feet and we are able to subtract out this 4 feet, then we're left with what's left. Again, if we look at it on this side, if we know that the entire side length is 10 feet, and we subtract the 4 feet, what we're left with is 6 feet. If the left-hand side of this bottom rectangle is 6 feet, then we also know that the right-hand side is 6 feet. Now that we have all of the dimensions of this figure, we can add them up and get a total combined perimeter of 60 feet. When we look at the area, we know that we don't have a formula that we can use to find the combined area of this figure. So we need to split it into 2 figures that we do have formulas for. In this case, we're splitting it into 2 rectangles. We know that to find the area of a rectangle, we need to multiply the length times the width. The length and the width of the left rectangle are 12 and 10, so we're going to multiply 12 times 10 to get an area of 120 feet squared. The dimensions of the right rectangle are 8 and 4, so we're going to multiply 8 times 4 to get a combined area of 32 square feet for the right-hand rectangle. If we add the area of the left rectangle to the area of the right rectangle, we get a total combined area of 152 square feet. Remember, area is in square units, perimeter is linear. Here's another example. So this is a figure inside of another figure. We want to find the area of the shaded region, which means we need to find the area of the entire larger rectangle, find the area of the smaller rectangle, and then subtract that out. So we're going to find all of this space. Remember, area is the number of square units that will fit inside the figure. So we're finding all of the total square units for the entire larger rectangle. Then we will take out or subtract the area of the smaller rectangle. Again, we'll use our formula for area of a rectangle, which is length times width. And we can determine the area of the entire larger rectangle is 502 4/4 square feet. If we find the area of the smaller non-shaded rectangle, we find that its area is 100 square feet, and if we subtract the non-shaded area of 100 feet from the entire larger rectangle, we're left with the total area for the shaded region of 402 and 4400 square feet. Looking at the set, we are again working with the perimeter of this polygon, but now we're including variables. So we know that we're not going to end up with one single value because we're not solving for the variable x. We're simply combining all of our side lengths, which means we're going to be combining like terms. In order to get it, we'll end up with an expression that represents the perimeter for this figure. Just like we did in the previous example, we're going to start with what we know. So we know this side length and we know this side length. What we don't know is this side length. We know that the entire top portion of this figure is the sum of this smaller side and this smaller side. So if we start with the entire side length and we subtract the length x plus 5, what we're left with will be the length of this portion right here. We know that when we subtract this expression that's in the parentheses, essentially what we're doing is we're distributing a -1 to each term within the parentheses. So we're going to be left with 2x minus 8. And then a -1 times x would give me -x. -1 times 5 would give me -5. Now I've got two terms that are x terms and two terms that are constants. I'm going to combine my terms that include variables to get x, 1x, and then I'm going to combine my constants to get -13. X minus 13 is the value of this missing side length. Now we're going to look at these vertical side lengths. Given the information that this side length is 3x minus 1 units long and this side length is 4x plus 2 units long, we know that this entire side length is the sum, or what we get when we combine this side length and this side length. So when we do that, we're adding our 3x's that we have here. Again, we're combining like terms. We're combining our terms with our variables. 3x's plus 4x's gives me 7x's altogether. -1 plus +2 gives me +1. And now I have the value for this left vertical side length. Now that I have all of the dimensions, I can simply add them all together. Again, we are combining like terms. I'm combining 2x's plus 3 more x's plus 1x plus 4x's plus 1x plus 7 more x's, and that gives me 18x's altogether. Next, I'm looking at my constants. -8 plus -1 plus 5 plus 2 plus -13 plus 1 gives me -14. So the perimeter of this figure is 18x minus 14. In the Go section, we are looking at finding rates of change for functions that are represented in different ways. So we're going to look first at the table. And when we're looking for the rate of change, it's how is that, these are for linear functions, and we know that they are increasing or decreasing at a constant rate. So we're trying to find that constant rate. When we're looking at the table of values, we're looking for what is the change in my output from one output to the next, and that's my numerator. And then we're looking at the change from one input to the next. So these are my x values, these are my y values. So we're looking at the change in the y values, and we're dividing that by the change in the x values. And so our constant rate of change, or our slope, is -3/2. When we look at this equation, which is written in slope-intercept form, also thinking back to Unit 1 and when we were looking at explicit and recursive functions, this is the explicit function. We know that our rate of change is our coefficient. It is the number that's being multiplied to the variable. So our change in our y values is 5, and our change in our x values is 2, and we know that this is the rate of change is decreasing. So we are either going down 5 units and then going to the right 2 to hit another point on our line, or we are going up 2 units and then going to the left 5 units, and then again we'll hit another point on the line. When we look at our recursive function, we know that our constant rate of change is positive 3. If you recall, f of n minus 1 represents the function or the output, the previous output. And that's looking at the right-hand side of our table. So we're saying, what are we doing to each of our previous outputs to get the next output? And in this recursive function, we know that we're taking each of our previous outputs and we are adding 3 to that. So we are repeatedly adding 3. Our constant rate of change, or our slope, is 3. And when we look at the graph, again, as in all of these, we are looking at the change in the y values divided by the change in the x values. So if I'm looking at any 2 points on this line, if I start with this point right here and I look at this point right here, I know that the y value for this point is 3. The y value for this point on my line is 1. 3 minus 1 is 2. I know that the x value for this point is negative 1, and I know that the x value for this point is 0. Negative 1 minus 0 is negative 1. And again, even though the negative is written in the numerator here, we know that this fraction bar represents the operation division, so whether we are dividing a negative by a positive, we'll still get that negative, versus dividing a positive by a negative, we'll still end up with the negative 2. So whether we go in the negative direction with our y values 2, and then in the positive direction with our x values 1, or starting at this point, if we were to go in the positive direction with our y values, and then in the negative direction with our x values to get from one point to the other, we would still have a negative rate of change, in this case negative 2.